questions before I start with a new topic? Okay. You don't want that right now, though, do you? You want to wait till you get it back, right? Let me see a vote. Who wants to wait until you get it back? That's like most people. Okay. That's over. Yeah, we're not doing it now. When are we going to get it back? I think it will be back next week. Yes, that's what I think. Okay, so the new topic is circular motion. Whoops. That's better. And we're going to use a lot of the stuff that we've already done, mostly in lab, thinking about how to break down the acceleration. That stuff will help a lot with thinking about this. So let's think about an object moving in a circular path. Imagine that's a circle. And the thing's going this direction around that path. And let's say that we're interested in the object here. And, let's say it's slowing down as it goes around this path. Then we know that the velocity vector is like this. That's always tangent to the path. Since it's slowing down, we know that the parallel part of the acceleration is that way. It's turning, and so we know that the perpendicular part of the acceleration is this way. And so the total acceleration vector is equal to the parallel part plus the perpendicular part. So we've done all that kind of stuff before. And I'll give some a general method for doing circular motion problems. But I want to point out at the beginning that there are really only 3 new things that we're going to do in circular motion. And 2 of those things are just new names for a parallel and a perpendicular. So that should be easy. And so here's all that's new for circular motion. First, in circular motion, a parallel is called the tangential acceleration. In the night class, I said that, and somebody in the class just laughed uproariously over that. It still sort of has me feeling a little unsettled. So I'll write that as A. Okay, so why is that called the tangential acceleration? Because it's a very simple reason. It's because it's a parallel and it's tangent to the circle at that point. So it's a really good descriptive name of what it is. These names only apply for circular motion, though, so we're still like, for general motions, we're still going to call them aparallel and aperpendicular. Second, in circular motion, aperpendicular is called the centripetal acceleration. Anyone think that's funny? The guy in the night class did not find that one funny at all. Yeah, yeah, either one of those would have kept him from doing that. Okay, it's a little funny. Centripetal. Now I get it. Okay, so why is that called centripetal? Well, that's, once I tell you that centripetal means toward the center, then it makes sense, because something that's perpendicular to a tangent line, if the shape is a circle, always points right towards the center. So that one even reminds you what direction it points. You don't even have to think about whether it points this way or that way with circular motion. It's always towards the center. And the last thing, so those two are just renaming things, but the last one is actually a calculation that we can do now that we never had before. The magnitude of the centripetal acceleration, that's not how you spell magnitude, magnitude is the speed of the object squared divided by the radius of the circle. So this v is the object's speed, and r is the radius of the circle. So the meanings of the tangential and centripetal acceleration are still just the same as they have been when we think about aparallel and aperpendicular in lab. The tangential acceleration is responsible for whether the speed is changing as the thing goes around the circle, whether the object's speeding up or slowing down. Have you guys seen Real Genius? The movie Real Genius? Have I talked about that in here yet? It's the most underrated 80s movie. And there are some really good 80s movies, you know, but a lot of them are really well known for being good. Like, yes, it's with Val Kilmer. Yeah. And it's kind of about, like, kind of like physics geniuses or whatever who don't fit in, you know. It's about finding your place in the world and things like that. It's really good. Has a really good soundtrack. There's a scene where they're all just they're just working all the time, and they're all sitting in the library studying, and all of a sudden one of the guys gets up and just starts screaming and just like storms out like he just finally cracked, you know. And they just all move his stuff aside and just keep studying, you know. Anyways, that's what I was afraid was happening when that guy laughed in class yesterday. But then I talked to him after. He seemed fine. But you should see it. Real Genius. It has two of the really, like, I don't know their names, but really recognizable, like, 80s bad guys. They were 80s bad guys in like 5 different movies each, you know. And also, you know, from Napoleon Dynamite, Uncle Rico is in it. That guy, I don't know his name either, but he's really good in it. So I really recommend it. Okay, so the tangential acceleration has to do with speeding up or slowing down. Centripetal acceleration has to do with turning. And we can think of this one as the acceleration that makes the thing move in a circle. Say makes the path circular. And the thing that's, so in general, the perpendicular part of the acceleration makes things turn. If the perpendicular part of the acceleration has a magnitude of v squared over r, that's what makes the path a circle. Okay? So any circular motion has this centripetal acceleration of v squared over r, but only circular motion where something's speeding up or slowing down has a tangential acceleration. And so let me go through a set of steps. So these are the general steps for circular motion problems. There's one type of problem that we're going to approach a little bit differently. So accept tetherball problems. For now, I'll just say tetherball. That's problems where something is just hanging from a cable and swinging around in a horizontal circle. So we'll address that a little later because there's a really nice, simple way to do that. But everything else, this approach works for. So the first thing you have to do is you have to choose where your coordinate system is. And since circular motions can be this way or diagonal or whatever, it's not just a matter of choosing where your coordinate system is on the page like this. You have to imagine like a view of this circular motion that's happening. You want to choose a view and a coordinate system where the motion looks like a circle. Okay, so what I mean by that is something's moving in a circle like this, then the view you want to take is looking at it from the side, okay? If the circular motion is like this, then the view you want to take is a top-down view, okay? Because if you have a circular motion like this, and you look at it from the side, you can't see that it's a circle, you just see that it's going sort of back and forth, you know what I mean? So you need to choose a view where you can see that it's a circle. The second step is to choose a point on the circular path that you're going to analyze. Okay, so if the circular path is this, then you can choose this point or and in some problems, what point you analyze is going to be given for you. Like it'll ask you something about what's happening when the object's here or here, And then other times you're calculating stuff that you could calculate based on any point. So you just have to choose one. Okay. And by far, it's going to be easier to do the calculations you'll need to do if you choose these 4 points that are straight in the positive or negative x from the center, or straight in the positive or negative y from the center. If you choose like this point, for example, to do your calculations, you're going to have to use tons of sines and cosines and stuff. You might as well just stay at one of these 4 points. I don't think there are any problems in the practice problems, tests, or anything that are anywhere other than those 4 points. So there's no reason you have to deal with that. But if you're curious about it and just fiddling around with it, you know, you might one time or something want to try one of these problems at one of those wacky points, and you'll see why you never ever want to do it again. Step 3, draw a vector from the chosen point toward the center of the circle. That vector that you're drawing is the centripetal acceleration. And the magnitude of that is v squared over r. So if this is the circular path, and you're looking at this point, there's the coordinate system. Then this vector here is the centripetal acceleration vector. So is that in the positive or negative x direction? Negative. And the magnitude is v squared over r. So a lot of times, probably most of the time, you'll be given these values or you'll be able to figure them out. So you can just plug them in, get a number, and then the centripetal acceleration vector in this case would be negative v squared over r for the x component and 0 for the y component. Fourth, find a tangential based on whether the object is speeding up or slowing down. If the speed is constant, then the tangential acceleration is 0, and that's called uniform circular motion. You know what it's called if it is speeding up or slowing down? What that kind of motion is called? Non-uniform circular motion. That was a terrible guess. Just terrible. Okay. Where was I? Okay, so now the total acceleration is the sum of those two. So centripetal plus tangential. Step 6, draw a free body diagram. And then step 7, Newton's second law. So basically, compared to the stuff we've been doing, we just now have information about the acceleration, and we can use that information about the acceleration to find out stuff about the forces that we couldn't if we didn't know something specific about the motion, you know. Any questions about that? I'll go through a couple examples. Question? Okay. Okay, so let's say that there's a plane. Thanks. That went better than in my night class. And let's say it's going through a circular path that's not drawn to scale. The center of the circle is here. The point that we care about is here. So this is one where you're told what point you have to deal with. We're given that the radius of the circle is 250 meters. So I'll call this point P. The speed of the airplane is 120 meters per second. And that's constant. So what does that mean about the acceleration? If it's a constant speed, what do we know? There's not going to be any tangential acceleration. Yeah. So we only have to deal with the centripetal. So is it uniform or non-uniform circular motion? Uniform. Yeah. And let's say that we are engineers at the company that has to make this plane, and we want to know a few things. So first, what's the acceleration of the pilot at P, at point P? And then related to that, I'll still call this part A, but we'd like to know if he would live. It's like that's all of the best airplane companies are careful about making sure about stuff like that. And then for part B, what's the force vector and for this problem, we're going to say we don't know the direction. Unknown direction. Applied to a 100 kilogram pilot by the chair. And why would a company want to know the force vector that the chair applies to the pilot? Probably they don't care too much about that, but what they would care about is what's the force that the pilot applies to the chair, because that's an important thing for determining how strong the bolts have to be and things like that. Like, what do they have to do to make sure that that chair doesn't break under the force that it's under in a case like this, you know? So now we want to use this to find what's the force vector applied to the chair by the pilot. So like maybe they're thinking of using a hammock instead or something, and they want to know if it'll hold, you know. We have B, how would we get C? So if we know the force vector applied to the pilot by the chair, what's the force on the chair by the pilot? Is that what you're going to say, equal and opposite? Yes. Newton's third law says we just have to multiply the vector by -1. Okay. Okay, so let's go through the steps just one by one. So first we have to choose a view where we can see the circular path, and that's the view that's shown in the problem. And I'll put the coordinate system here. And then we're told that we have to deal with this point, so put that there. The plane's going counterclockwise around this circle. So what way would the velocity vector be? Yep, straight up. Excuse me, that's not listed in the steps, but that's true. So now that we have the point and we have the path, now we draw a vector from the point of interest toward the center. And that's the centripetal acceleration. And we can also calculate the components of the centripetal acceleration. The magnitude is equal to v squared over r. So that's 120 meters per second squared divided by the radius of 250. And that's 57.6 meters per second squared. That's pointing in the negative x direction in this case. So write that as an acceleration vector. That's negative 576, nope, 57.6. Negative 57.6, 0. And the units are meters per second squared. Okay, so now we're done with part A. We wanted to calculate the acceleration. We also want to know if he'll live. Anybody have a feel for whether someone can survive that acceleration? Well, think of it as 9.81 is g. So this is just under 6 g's of acceleration. So when people talk about g forces, g acceleration, this is what they're talking about. Can somebody survive an acceleration of 6 g's? Yeah, I think that's getting to the point where if it lasts very long, you can pass out. But for a fairly short duration, just a few seconds or something, that's not that big a problem, I think. I saw a special on Nova once about pilots. I watched it for like 5 minutes, and they said something like that. Oh, okay. And so, yeah, if you're like flying a fighter jet or whatever, those planes are all easily powerful enough to create enough of these g-force, these g-accelerations to make any pilot pass out easily. And obviously, if you pass out while you're piloting a plane, that's really, it's a bad prognosis. And so the pilots have to be like really careful. Like they have to know how fast they can turn. Like how, like apparently that's a big thing that you have to. It's a major concern for people flying like military type jets, you know. For now, eventually you'll die. So now we want to calculate the force applied to the pilot by the chair. Well, you know, let me flesh this out a little bit, actually. So why did I said that's the centripetal acceleration. What about the total acceleration? That's what really matters. Well, the total acceleration is the centripetal plus the tangential. This one's 0 because it's a constant speed. And so the total acceleration is negative 57.60. So now that we have the acceleration, now we're going to draw a free body diagram of the pilot. The point that we're looking at, the plane's going straight up into the air, right? The nose of the plane would be going up. So the pilot would be sitting, you know, the pilot's back would be facing the ground. So a free body diagram would look something like this. You know, there's the feet, leg, the pilot's sitting here like this. That's a helmet. Okay, so what forces are acting on the pilot? Yep. And we said the mass was 100 kilograms. So 100 times 9.81 is 981. And then we don't know the direction of the force vector that the chair applies to the pilot. So I'm just going to give it an unknown x component and an unknown y component. So I'll just put a force here that I'll call fx and a force here, fy. I just put them in the positive x and positive y direction. Those are that's the x and y component of the force applied to the pilot by the chair. So we're trying to calculate those two components. Yeah, right. And we're assuming that his feet are also on part of the chair, I guess, you know. So we're just lumping it all together. And so the pilot's not touching anything else. So now we can go to Newton's second law. I'll combine fx and fy into a single force vector. So fx, fy. Plus the weight force, 0, negative 981. If there's a normal force, like acting on his foot or, well, so yes, there's a normal force somewhere on his chair, like on his butt. I just drew it in the positive x direction because we don't know the direction, but most likely we would imagine that the force is going to act like a normal force. We'll just calculate the directions of both of those two components. The signs will come out in the math. And then those are equal to the mass times the acceleration vector. So 100 times negative 57.60. The x equation says fx is equal to negative 5,760. And the y equation says fy minus 981 is equal to 0, or fy is equal to positive 981. So now if we put those back into the force vector, the force on the pilot by the chair is equal to negative 5760, positive 981. So what does that force vector look like? If you draw the coordinate system, you can just plot that as a point, and that'll give you the head of the vector. So it'll be in the negative direction, negative x direction, and a little bit in the positive y direction. So maybe like this. That's the direction of the force vector applied to the pilot. Yep. 5760. Because in part A, we calculated the acceleration was this. And so fx is equal to 100 times this. So this arrow is pointing in the positive x direction, so that you can think of that as the x component of that force. And this one's pointing in the positive y direction, so you can think of that as the y component of the force. Yep. So that's something you can do anytime you don't know anything about the direction of the force. That doesn't happen in this class very often, but that's always, you can do that if you don't know the direction. Okay, so then for part C, as the people designing this plane, what we really want to know is the force applied to the chair by the pilot, so we can figure out the materials to use in construction. So the force vector on the chair by the pilot, Newton's third law says it's just going to be equal and opposite to this one, because that's just a contact force. So we have a positive x component of 5760 and a negative y component of negative 981. And that's just in the opposite direction of this one, so it's going something like that. Okay, so let's think about these two. So there's the pilot, and here's the chair. The force vector on the pilot by the chair, we said, is going something like this direction. The force on the chair by the pilot is going the opposite direction, something like that. So are these two things pulling on each other or pushing on each other? They're pushing on each other. So is the pilot going to feel like he's coming out of his chair, or is he going to feel like he's being smashed into his chair by this acceleration? Smashed into it, yep. He's being pushed down into the chair, and the chair is pushing back. Any questions about that? There's something new that we haven't seen before. Something new. And that is that, you know, because we can, in these kind of problems, a lot of times, you know, we're changing the view that we have of the motion, because we're always taking the view that lets us see the circle. Anytime we take a top-down view or a bottom-up view of a thing, it's true in either case. I'll just say a top-down view. So that would be like if the circle's horizontal, parallel with the ground. And so we're going to take a view in a coordinate system that looks down from above. Okay. Now, so this object's moving in a circular path like this, and every object has weight acting on it, right? But now, what direction does that weight point? Well, down. That was a dumb question. But the coordinate system's like this, you know? And now the weight is going to be this way, out of the plane of the coordinate system. We haven't seen that before, okay? So when that happens, any force that isn't in the plane of your coordinate system, you can just leave out. So it's not like weight isn't acting, it just isn't acting in your coordinate system, you know? So whenever you take a top-down view, you can ignore the object's weight. And often, if there's a normal force, like the thing sitting on the ground or on an object, you can often ignore that too. You can do that because those forces are out of the plane. They don't show up in our coordinate system. That's because they're out of the plane of the coordinate system. Okay, so let's do another example, and this is one where we'll see that. So let's say a ball is moving in a circular path like this, along a smooth table, like imagine this is a glass surface or something. And it's connected to a post in the middle. And it's going around this circular path at a constant speed of 6 meters per second. So this ball is rolling along this surface. radius of this circle is 0.25 meters. And the mass of this ball is 60 grams, or 0.06 kilograms. That's about the mass of a pinball. And we want to know what's the tension in the string. Okay, so first we want to take a view where we can see the circular path. So that's a top-down view in this case. So that's the circular path from above. And I'll do the coordinate system like this. And in this problem, it doesn't give us a location on the path that we have to deal with, so we get to choose. Like I said, I would always choose this or this or this or this, but any of those is fine. Just to do it a little bit different this time, let's do down here. But this would work out exactly the same way, get the same answer any place we chose. Centripetal acceleration direction is towards the center. So it's in the positive y direction. The magnitude is 6 squared divided by the radius. So that's 144 meters per second squared. So to put that in a vector, the centripetal acceleration vector is 0, positive 144. This is moving at a constant speed, so there's no tangential acceleration. So the total acceleration is just equal to 0, 144. Now do a free body diagram of the ball. Okay, so forces are acting. There is a weight force. You know, everything has a weight force. But in this picture, what direction would the weight force be pointing? Yeah, into the page. And, you know, if our coordinate system is like this, it's like how far in X and how far in Y do you have to go to get a vector that goes straight into the page? There's no answer to that. There's no way to get from this coordinate plane into that direction, so we can just leave it off. Okay. And then what about the normal force? There's contact between the glass surface and the ball. Which way does that point? The opposite, out of the page. And so we can just leave both of those off. Okay. Is there anything else making contact with the ball? The string, yep. And it's a pulling force, so that would be going straight this direction. And by the way, there is a way to represent forces that are into and out of the page. You don't have to do it, but if you want to do it, you can. You treat it like if it's coming out of the page, coming towards you, you draw like a sort of a simple picture of an arrow coming towards you. And if it's going into the page away from you, you draw basically like the feathers of an arrow leaving. So you could draw this with the cable force like that. The weight force is going into the page. So that's how you draw the feathers, just a circle with an X in the middle. That would have the weight. And then the one coming towards you is the normal force, so that's a circle with a dot in the middle. But either way, neither of those would show up in our vectors when we did Newton's second law because they're in a different plane. Okay, so Newton's second law says the only force that shows up in this coordinate system is the cable force pointing in the positive y direction, so 0t, and that's equal to the mass, 0.06, times the acceleration, 0, positive 144. So the x equation says 0 equals 0, and the y equation says t is equal to, if you multiply these two together, 8.64. So the cable tension is 8.64 newtons. And if you choose a string that can't hold that much weight, can't support that much force, the string would break. You know, so those are exactly the kind of things when you're designing something as an engineer that you think about. You figure out what kind of forces are required, and then you use that information to figure out what kind of materials you need to use. Any questions about that one? Okay, let's do the quiz and get out of here.